Hi, I'm Yixun Wei. Today I'm going to talk about the work we did at the University of Minnesota. It's an encoding scheme to enlarge practical DNA storage capacity by reducing primer-payload collisions. DNA is famous for its ultra-high storage density, and you could encode binary data to multiple DNA payloads. For each payload, you could append a primer pair to serve as a unique address. And in the future, if you want to read some data back, you can use PCR to amplify only the target DNA sequence with specific primers, and then you can sequence in the target data back. And during the procedure, PCR is very vulnerable. A standard PCR involves with the denaturation of the double helix DNA strand, and then you can put complementary primers into the solution to bind with the target primer, and then the target DNA sequence can be elongated and doubled. However, if there are some irrelevant DNA strand, as in subsequences that is similar to the target primer, then those irrelevant strands can be bind with the complementary primers and causing wrong amplification. In this case, those primers must be disabled to guarantee a safe PCR, and that will cause a huge capacity reduction. So to relieve this impact of the collision, we propose a collision-aware encoding schemes here. In this scheme, every bit triplet will have 4 predefined DNA-based triplet candidates, and we select the most proper one based on the previous 17 already encoded DNA base. We encode the payload with a primer-payload reduction pattern. This pattern is concluded from the analysis of primer pattern. So for more details, please see the presentation.